Thank you very much. First, I would like to begin by thanking the organizers for inviting me to this wonderful meeting. I will talk about something which looks like it doesn't belong in a statistical physics meeting, but I will convince you that there is some statistical physics in here. The title of my talk is Insights from a Pseudospectral Study of a Potentially Singular Solution of the Three-Dimensional Axisymmetric Incompressible Euler Equation, Tigers and Thermalization. I will explain all those words as I go along. All right. So this work would have been impossible without these students. Sai Shweta is in the audience, so she will be able to answer all your hard questions. Puneet Sharma started on this as an undergraduate and is now about to finish his PhD at the Max Planck in Göttingen. And we have had many, many, many discussions with all these people, especially Uriel Frisch and Shamriddhi, who had to go to Kolkata. And we are very grateful for support from various funding agencies, CSR, SERB, the National Supercomputing Mission, the Indo-French Center for Applied Mathematics, and our Supercomputing Center. So first, this is the most important slide in my talk. So congratulations, Deepak. You have been a role model for us, and we look forward to continuing to work with you. And also, I would like to record his great contribution in setting up, along with Mustansir, a great school of physics from TIFR. And now their students are all over the world. And today, many of them are gathered here and have organized this meeting or have spoken in it. So thank you very much. And more power to you, Deepak. Okay, here is an outline of my talk, history and motivation. Then I will tell you a little bit about models and the methods we use, which are Fourier-Chebyshev spectral scheme. I will spend some time on conserved quantities. And then there are various singularity detection criteria, which are used in these sorts of partial differential equations. There's a celebrated one due to Beale-Kato and Majda. And then there are these things called tigers. You can blame Shamriddhi for the name, Shamriddhi and Uriel Frisch, but I'll tell you what they are. And then there is thermalization. So you see that statistical mechanics is creeping in, and the analyticity-strip methods that we use, and then conclusions. All right. More than 265 years ago, I wrote 265 actually years. So 267 years ago, Euler wrote this celebrated paper, The General Principles of Movements of Fluids. And perhaps it's the oldest field theory ever. I don't know, somebody can correct me if necessary. The trouble with the field theory was that it's nonlinear, and so one couldn't make very much progress. And even to this day, progress is limited. So here is a quick bird's eye view of what we know and what we don't know. So solutions of the two-dimensional incompressible Euler equation with analytic initial data do not exhibit a finite time singularity. It is, however, not known if any solutions of the 3D incompressible Euler equation or its viscous descendants, namely the three-dimensional Navier-Stokes equations, develop a singularity in finite time if we start with analytic initial data. And even if we restrict ourselves to the Euler equation, the answer to this grand challenge finite time singularity problem will have implications for turbulence in fluids. This was first conjectured by Onzaga, who said that if the velocity field is not sufficiently regular, he specified some Hilbert properties. Then the solution can dissipate energy, even though you're starting with the Euler equation. And there's a nice overview of that in this paper. Now, What about 3D Euler? What's known here is a summary which John Gibbon gave in a meeting in 2005, which was published finally in 2008. And there have been various explorations of finite time singularities of the Euler equations in 3D, which have not yielded unambiguous results for or against the singularities of the 3D Euler equation. So many of these investigations are numerical because you use numerics to gain some intuition for when you might have singularities. And he had a long list of people who have got singularity yes, singularity no, and some people have published on both sides, which is not to say that these people don't know what they're doing. It's a way of saying how hard the problem is. All right, in 2014, there was this paper by Luo and Hao in which they came up with an interesting initial condition. So that is the problem that we will look at. We will not look at this 3D Navier-Stokes PD at all, which is one of the Clay Millennium problems. I hope one of the people in the audience will solve it eventually. But here they looked at a potentially singular solution of the three-dimensional axisymmetric Euler equations. All right. And given the importance of the problem, I mean, they used some they used a hybrid Galerkin and finite difference method. And given the importance of the problem, it behooves us to check it with some other numerical scheme, which is what we will present here. And they use the celebrated Beale-Kato-Majda criterion, which I'll tell you about as we go along, to use some other criterion also to see that this potential singularity is not just an artifact either of the numerical scheme or of the singularity detection criterion. So the singularity detection criterion that we will use is perhaps first used by Sulem, and Ehlenfrisch, which uses a pseudospectral study. I think the pseudospectral study they did was for the one-dimensional Burger's equation. We will do, of course, a much more complicated study using a Fourier-Chebyshev scheme. You go to complex space, and then you see at what rate the energy spectrum goes down. I will tell you what that means as we go along. And it requires a pseudospectral simulation. Now, where does statistical mechanics come in? It comes in these two old papers, the first due to Hopf. You see in the title of the paper, they used to allow you to put the equation in the title. So this is the Burger's equation, the partial derivative of u with respect to t, one dimension, ux, uxx. And then another paper by T.D. Lee, who looked at ideal hydrodynamics, that is Euler, and its MHD analog. And they said that the moment you spectrally truncate it, you will have a finite number of modes. And if, roughly to make a very long story short, that at sufficiently long times, the system must thermalize, and there should be energy equipartition. And for the 3D Euler case, that implies for the energy spectrum of the fluid that the energy scales as k squared. Those of you who know about Navier-Stokes turbulence will say that's not what Kolmogorov told us. There should be a k to the minus 5/3 spectrum. So where's the difference? The difference is this is a thermalized spectrum. And the best illustration of this was carried out in this important paper by Sicholas, Bonaiti, Debache, and Marc Brachet at the École Normale in Paris. And so here is a high-resolution Euler simulation. On the vertical axis, you see the energy spectrum. The upper one is some difference in the resolution. This is low resolution, that's high resolution. So as time goes on, you see that a tail is developing at large K. This is the log-log plot. And this is the K-squared spectrum. So at large K, the system starts thermalizing. The prediction of Lee comes true. And on intermediate scales, this acts like a thermal bath for the rest of it. So for intermediate times, you see a -5/3 spectrum until the thermalized spectrum consumes the whole thing. And you will hear in Mahendra Verma's talk later today the complexities of this argument in 2 dimensions. All right, so down to what we are going to do. That's the 3-dimensional Euler equation. U is the velocity field, omega is the vorticity because of this formulation. And we also use a vector-valued stream function psi, to which the vorticity is related by a Poisson equation. In this formulation, the pressure drops out, but we can calculate it if we want it. All right, so this is not the problem we are going to work on today. This is still unsolved. We do not know whether there is a finite time singularity or not. We will look at this axisymmetric flow. So it is useful to go back to cylindrical coordinates. These are the unit vectors. And please take my word for it, the algebra works out. It is also advantageous to take these components, u theta, etc., and divide them by r to define new variables u super 1, omega super 1, and psi super 1 for the theta components. Okay, and then believe me that when you put that in the original Euler equations I wrote down, this is the set of equations you have to solve, and the Poisson equation has become this, right? Now, I mean, for those who are easily scared, this is a daunting set of equations. But if you have enough patience and skill, you can actually solve it. And I'll tell you how we solve it. All these variables are well defined. I'm pretending to be half a mathematician here. So I'm writing down all the complete conditions on when things are smooth and so on. Furthermore, these theta components must vanish at the origin for this thing to be smooth. And we will solve the above equations in this domain, which is bounded in R from 0 to 1, 0 to L in Z, but periodic boundary conditions in Z. And it's axisymmetric, so I don't need to tell you anything more. And subject to L periodic boundary conditions, no flow condition at the boundary R equal to 1, and we must respect these pole conditions, all right? And what Luo and Hao found, that with these initial data, that is, so you see U1 was related to U theta, they put in this complicated looking thing. Yes? Just definition, running out of symbols, that's all. They used it, so we use it. No significance. Okay, just definition. U theta divided by R. Okay. All right, so these are the initial data. So all of you who have studied mathematical physics in your lectures, especially the students here, you know that when you see such a problem, you want to solve it pseudospectrally, you have to do Fourier-Chebyshev. Let me remind you that if you were just doing ordinary periodic Euler, you would just do Fourier, and then the pseudospectral method means that you evaluate derivatives in Fourier space, and you evaluate products in real physical space. You go back and forth using fast Fourier transforms and so on. Well, here it's in principle the same, but in practice quite a bit more difficult. So you take any function of R and Z, you have to expand it in a Fourier-Chebyshev representation. That's the coefficient, e to the I k z, and these are the Chebyshev polynomials of the first kind. And if you keep track of everything and you look at the collocation points, they're scrunched up near R equal to 0 and R equal to 1. Okay, This is just a heat map of the vorticity. All right, so if you want all the details, they're in this paper, or in the break, you can ask Sai Shweta. She knows all the details because she did the calculation. Okay, here is a qualitative picture of the flow we are looking at. I gave you that initial condition. So if you look at this in this domain, that's the Z direction. U is periodic in Z. U dot N vanishes at the boundary delta omega. And there's a symmetry plane, Z equal to 0. Above it, there is a velocity going this way and that way. That's the U theta. So this is often called swirl. And then this thing sets up a secondary flow of this sort. And here is a point which looks like a stagnation point. And this is the sort of intuition that these applied mathematicians have. Of that point is where we might get a finite time singularity. So that's at R equal to 1, Z equal to 0. Yes? Yes. That's the initial condition. No, it works out. There'll be another one. There'll be another one at the other end. Yeah, that's fine. It's specified completely by the formula. This is just a cartoon. Okay. Yes. Nothing. We're not going there at all. I mean, this is perfectly well-defined PDE with suitable boundary conditions. Nothing outside R equal to 1. Okay. Yes. We have. U dot N is equal to 0. We'll see. Give me a few minutes. Okay. So if you have a good code, you must conserve the energy and the helicity. And this is the celebrated Beale-Kato-Majda theorem, which says that, a singularity might arise by some 240th derivative of the velocity becoming singular. Okay, but they found, and that's the importance of this theorem, that if you look at the L infinity norm of the velocity of the vorticity, then so long as this integral is less than infinity up to some time capital T, then no finite time singularity. But the moment it becomes infinity, then you have a singularity. So often people who test for singularities using this Beale-Kato-Majda criterion do this log of omega infinity and look at it as a function of time, which is what Howe and Luo did. Now it turns out there's another set of equations which is a 1D cartoon, and I'll motivate it perhaps in the discussion if necessary, where you look at just this set of equations for some fields U and omega and V, and H of omega is a Hilbert-transform, and you use this initial condition. This not follows is a cartoon of the singularity that we will see later. And there is a long history of such Hilbert-transform models going back to Konstantin Lax and Majda, and it's been suitably modified for this problem by Howe and Luo. So this is how they're related to the U1s, omega 1s, and so on. And we restrict ourselves to the boundary at R equal to 1. So we only look at the Z dependence. Okay, so, all right, pseudospectral investigations, this is what we will be doing. So we will, when you look at potentially singular solutions, you get localized oscillatory structures, which were called tigers in the paper that I will show you. They were first introduced in the context of the one-dimensional Burger's equation, which of course has a finite time singularity, and the two-dimensional Euler equations, which do not have a singularity or route to thermalization. And I should also point out that just because you have tigers doesn't mean you have a singularity. So here is the paper, my good friend who's in Kolkata today, Shamriddhi, Uriel Frisch, Nazarenko, and Matsumoto, they found. So this is a little bit after the shock has formed, and you see the structure. If you blow it up, you will see a lot of oscillations. This is the structure they christened tigers. They had some literary allusion to William Blake. You can read their paper for that. But that's the tigers. Note that it is not appearing near the jump or the shock, but away from it. So it's not a Gibbs phenomenon. It has to do with some resonant interactions between a wave that is set up because of the Galerkin truncation at some wave number k sub g interacting with fluid particle velocities in a resonant way. Okay, that's not entirely clear what I said, but please read their paper. All right, so now the analyticity-strip method says that if you have a DNS, so let's just do a periodic domain, okay, none of this axisymmetric business. Then if you complexify space, then it's not as if the singularity comes from somewhere, just out of the blue. It comes from the complex plane, and its signature is easy to pick up if you look at the Fourier transform of the velocity. There's a parallel part which is not very important, but there is an exponential decay. And if you watch this with delta, okay? Now this delta depends on time. And as the singularity approaches the real axis, you get a finite time singularity, which is signaled by delta t going to 0. So this is what we have to generalize to the 3D axisymmetric domain. I will not give you every detail, but we have done it. And of course, this determination of delta is accurate so long as it's of order of few mesh sizes. And that's also the time at which the tigers appear. So, yes. Yeah, of course. Yeah, it will. Sure. If V has it, vorticity will also have it. Yes. So, okay, if you're doing a very careful calculation, I just want to show you that what my students do is not entirely trivial, okay? You have to check for errors, because now, when you're doing this axisymmetric thing, you're solving a Poisson equation. Solving a Poisson equation is absolutely trivial when you have periodic boundary conditions, but it is not so trivial when you have this sort of boundary conditions. So you better check your code carefully, which of course Shweta has done. And she has actually used 2 Poisson solvers. And the essential message of this slide is to show that both agree, whether you look at the percentage change in the energy. In any practical calculation, energy is not completely conserved, nor the helicity and so on. And this is the beginning of the singularity you see using the Beale-Kato-Majda criterion. It's going to blow up. This is log of omega infinity. And both the Poisson solvers that we have used, or she has used, give the same results. You can check it with test functions, which I will not go into details. You can also validate it against, and this is important, you know, when you write a new code, you must validate against what is known. And there was this stationary solution of the axisymmetric Euler from the group of de Broglie, and it looks complicated, but you can sort it out, and then you can check that your numerics is getting it right. I'm not explaining everything, but it does get it right. Now let's look at the 3D axisymmetric Euler with the boundary conditions I specified and the Luo-Howe initial condition done pseudospectrally, not by their method. And here is energy conservation percentage, pretty good until some time. Helicity more or less 0 until some time. And here is the Beale-Kato-Majda criterion plot. Log of omega infinity going up. This black dashed line is the time of the potential singularity that was found by Luo and Howe. I show you here 2 other dashed lines. The brown line over here is the one at the time visually at which tigers appear in the vorticity, the velocity omega 1. And in fact, they're born in the vorticity even earlier. Okay, so our geospectral code is doing the right things. And these are the spectra, they're generalizations of the conventional energy spectrum. So you can keep the R constant and do a Fourier transform in K and investigate this, or you can keep Z constant and investigate the Chebyshev index M and look at these things. So if you look at these spectra, so let's just look at one because time will run out eventually. This is at fixed R equal to 1, that's the boundary, as a function of K. And this is a semi-log plot. So that's the exponential decay from which we can get the width of the analyticity strip delta T. And as time progresses, it goes up. There's some oscillation here, which has to do with asymmetry in the initial condition. So if you are fitting envelopes, you can fit the odd K envelope and the even K envelope. And here you see it's risen completely. So this is thermalization because you're looking at only one direction. The appropriate power is K to the 0. Okay, so that's K to the 0. And if you look in the Chebyshev direction, there's a similar thing, which I won't bother you with. If you look at one-dimensional burgers, this is what thermalization looks like. That's K to the 0, and these are the data well after the shock has formed. This is the one-dimensional Hilbert model that I told you about. Not perfect, but the Hilbert model, the Hilbert-transform model, has various peculiarities, which I'll be happy to discuss with you later if you want. So it's not a surprise that it's not completely K to the 0. And this is our 3D axisymmetric Euler. This is as a function of K with fixed at R equal to 1. That's K to the 0. And this is summed over all R. Okay, that spectrum, and that's K to the 0. So of course it's noisy. And to make life difficult here, there is a potentially finite time singularity. And that really complicates the numerics.
So, Rahul,
yes.
Yeah.
Yes.
So is this still truncated or
everything is truncated?
No, but I thought 1D burgers, you said it goes as K square.
No. 1D burgers is K to the 0. It's 3D Euler, which is K squared.
Even the truncated burgers, I thought you said it thermalizes, right?
Yes. I mean, that's the quality of the data.
Oh, this is energy already. Okay. So that's, but you said, I thought K square.
No, K square is 3D Euler.
Oh, right. Okay.
Okay. I mean, just equipartition. Sorry, Deepak, you have a question? Yeah. Yeah, that's standard. I mean, if you look at the spectra and turbulence, you have log plots. This is instantaneous at t equal to 17.001 because we are looking at time evolution. Right? And the Burger singularity has already happened. And at this stage, you're not solving a partial differential equation. You're solving, if you like, microcanonical evolution of the spectrally truncated system, for which actually in that case, you can prove energy conservation. And that's a result due to Majda and Mofinev. Okay, so let me just show you one movie. I won't trouble you too much. So here you go. This is on the vertical axis log of S1 and K and R. So that's how it thermalizes. Okay. I can show you more later if you like. Okay. Now, where are the tigers? So now we are going to take a section at R equal to 1. So this is U1, which is U theta divided by R as a function of Z. And again, away from the points where you get the sudden change, you get these oscillatory structures. And if you zoom in here, you see the oscillatory structures. They appear even earlier in the vorticity, so omega 1. Again, zoom in, you see these oscillatory structures. Well, before that, from the decay of the energy spectrum, you can extract a sort of birth, excuse me, that I'll come to later. This is the birth time of the tigers, just visually, or a MATLAB program. So you can see that this is how it changes with the Galerkin truncation wavelength, so 2 pi over kg. Okay, and there are similar plots that you get in burgers and so on. So to make a long story short, since I shouldn't go over time, the 1D Hilbert-transform model is doing its job of being a simple cartoon for this more complicated 3D axisymmetric Euler, and you have this variation, and you have the tigers, and so on. And here I show you for the first time, I'll show you in more detail for the 3D Euler, a plot of the width of this analyticity strip, the delta versus time, and it's going to 0. And here, whatever analog it has of thermalization, the energy spectrum, with the passage of time becomes flatter and flatter. But this is a peculiar model, so I don't want to spend too much time on the thermalization aspect here. Okay? So you can look at spatiotemporal evolution of the tigers by nice plots like this, which has been done in other cases. So this is time, and that is space, and that's a field coming out. And in burgers, everything is nice and sharp. And in every other model, it is much more complicated than burgers. That's the essential message of this slide. And you can look at how these tiger fronts propagate. Now you can look at these log decrements of the way in which the energy spectrum goes down. And you can look at it at various times, various sections R or Z. And if you look at the Chebyshev direction, this thing falls fastest at the wall, and the other one falls fastest at Z equal to 0. So from such things, you can find the width of the analyticity strip for the 3D axisymmetric Euler. So how are we doing relative to how Luo and Howe? This was their estimate for the singularity time. And we can do a fit to that time, and it works pretty well. So I would say this is an independent check of this potential finite time singularity. Of course, they could go to much higher resolution because they were using an adaptive grid. But then people said, oh, is it an artifact of that adaptive grid? So essential message is no. You can analyze it by a completely different numerical scheme, which is a pseudospectral Fourier-Chebyshev scheme. And you can analyze it using this analyticity strip method and get results which are completely consistent with their results. You can say, let's not bias it by looking at their results. Let's look at our data and find our estimate for the singularity time. And we get a reasonable number, which is in agreement with theirs, but not as many decimal places because we do not use an adaptive grid. Okay, so this is more details than I'm, okay, this is the fit, so to show you that we've done some real. Now, there have been recent related studies, which I should also mention. One is by Dwight Barclay, who also did a Fourier-Chebyshev thing, but his approach was, look, I believe they have the singularity, and he was right. But let me see if I can come up with a physics understanding of it. So I highly recommend that paper. He relates it something called a teacup singularity, which of course requires a boundary layer, but don't worry about that. And a problem that even Einstein worked on. Okay, and then there is another one due to Tobias Hertel, a graduate student, Nicolas Bess, and Uriel Frisch, where they used yet another scheme called a Cauchy-Lagrange method, which I cannot explain in 17 seconds, but which does get around the Courant-Friedrichs Levy condition because it's a semi-Lagrangian scheme. So, and all these studies agree that there seems to be a finite time singularity. So here are my conclusions. We have developed this Fourier-Chebyshev scheme for this 3D axisymmetric Euler case. We have also studied the one-dimensional Hilbert-transform model. We demonstrate that, first of all, the time of singularities is preceded by the formation of tigers, which are, if you like, a precursor to thermalization. But nevertheless, even though at that time we are not solving the PDE, by using this analyticity-strip method, we can extract the time of this potential singularity. And so there is now good evidence. This is different from 3D Euler, where people still cannot agree numerically whether there is a good enough initial condition which leads to a finite time singularity or not. And now, of course, a formal proof is required and is being examined by mathematicians. And from a statistical mechanics point of view, these systems provide good testing grounds for the study of tigers and of thermalization. So with that, I thank you. And I thank you for your attention. A movie was supposed to work here, but somehow it's not working now.